Now we can take our points, our complex numbers that we kind of consider in rectangular form, and convert them over into a polar form. So let's look at that. So I have some point I just put in the first quadrant. I was able to label some of the things like r is the distance or the absolute value, but the distance from the origin to the point. Drew a right triangle, which allowed us to give us some right angle trigonometry components to that. And let's start to build some of the things we know. What do we know? We know that r equals the square root of a squared plus b squared. We know that the cosine of theta, in this particular case, if theta is right here, is b over r. And if we want to rewrite that, we can write that as b equals the cosine of theta. I should put the r right there in the front. We know that there's a sine function we can build as well. So the sine of theta equals the opposite over the hypotenuse, which is an a over an r in this particular case. I could likewise solve that for a. And that equals r times the sine of theta. And then there's also a tangent function that we'll find useful at times. So the tangent of theta equals an a over a b. So those are some additional things that I think you would agree with us that, or with me, there's not two people here I don't think, but agree with me that, okay, those are reasonable. We know those things, and I can see those things applying here on this complex plane. So let's use that then, and let's rewrite our rectangular form. So our rectangular form, z equals a plus bi, let's rewrite that into polar form, where now that I have an a defined right here as r sine theta, and then plus an I, I'll put the I first, and then the b, which is r cosine theta. From there, I have r's in both those terms, so let's just factor that r out. So it's r times the sine of theta plus I cosine of theta. What we'd like to do right now is to learn how to convert our complex number that's kind of in a rectangular format into a polar format. So I designated some point out in this first quadrant. From that, I developed a right triangle. And from that right triangle, we can start to convert using some of a right triangle identity and convert some of the components from rectangular to polar form. I know what r is. R is the distance between the origin and this point. We can find that out. That's typically r equals the square root of a squared plus b squared. I know that I have a cosine function embedded in here. So the cosine of theta is my adjacent over my hypotenuse. And I can rewrite that in terms of a. So that would be a equals r cosine theta. I can do that for sine theta as well, you're right. So let's try that. Sine of theta equals my opposite over my hypotenuse. And also, let's solve that for b. If I can spell sine theta, unlike cosine theta. And there's another one that we're going to find useful as well, and that's the tangent of theta. So let's just kind of do that one right now. We're going to keep that in our back pocket for a little bit. So those are some of the general relationships that we can form as we look at both the polar form and also to the xy, the rectangular form. So let's begin with our point in complex form, which is z equals a plus bi. And let's rewrite that in terms of polar forms, which means in terms of r's and thetas. So z equals, I can keep the z. A we designate as r cosine theta plus b times I. B is r sine theta times an I. Cleaning it up a little bit, I can take an r out of both sides. or factor an r out. And what remains is r cosine theta plus, I'm going to write the I first, sine theta, just so I don't get that confused and include that I within the argument. And what we have here is we have the polar equivalent of the rectangular form of the complex number. And what we're going to learn to do is how can we use the polar form of a complex number to discover some things as we progress. So let's take this example where we have some point listed in the third quadrant on the complex plane where z equals -2 plus 2i. And I want to convert that to the polar form of a complex number. We begin with understanding that we have a rectangular form and that we already derived the polar form. And there's a couple other ones that are good for us to be aware of, where a equals r cosine theta and b equals r sine theta and the tangent of theta equals b over a. So what do we do? Where do we begin as we learn how to identify this one? Which means that we need to take our complex form and rewrite it in terms of r's and thetas. Well, we know that r, oh, I don't have that one up there. That one would be good to know. There we go. Now we can do it. So r equals a squared plus b squared. In this term, our a equals a -2, and our b equals a -2. So r then would become -2 squared plus -2 squared, all over the square root. That's 4 plus a 4 is a root 8. And that equals a 2 root 2. So r equals root 2. Now we need to identify what this theta is that comes and shows that particular position. And I think the tangent of theta will be our best way. So the tangent of theta is b over a, so -2 over a -2, which equals 1. And what tangents of what angles produce a 1? The tangent of pi fourths. So we know now that theta equals pi fourths. But pi fourths is an angle that's in the first quadrant. And my other tangent, or this angle, is in the third quadrant. So how do I get the angle that's in the third quadrant? Well, with tangents, we know that we add n pi to that. So that's every n pi. So let's just add 1 pi to that. So theta would equal pi fourths plus, we'll say it's a 4 fourths pi. That's 1 complete pi, which equals 5 fourths pi. And that is an angle that extends into that third quadrant. And that shows us that we have the correct theta now. So given that we have r and we have theta, we're now able to rewrite our complex number that was given in rectangular form to write it in polar form. So z equals, I start with an r. R was 2 root 2 times the cosine of theta. If I can draw a 5. 5 fourths pi plus I sine theta. And that was 5 fourths pi. Kind of got bounced out and crowded out by my rectangular form when we did that. So z equals -2 minus 2i in rectangular form is the same thing or equivalent to in polar form as 2 root 2 times the cosine of 5 fourths pi plus I sine 5 fourths pi. And we can start with a complex number written in polar form and return it back to, or well, maybe not return it back to, but convert it to rectangular form. So let's go through and chose cosine of 60 degrees. We know that exact angle, that is, or the exact value is a 1/2. And the sine of 60 is also another exact value that we are aware of, and that's root 3 over 2. From there, I can multiply that 2 all the way through. So I have 2 times 1/2, which is a 1, plus an I times a root 3. And there we have our rectangular form of z equals a 1 plus, and I'll put the I in front of the root 3. I'll make a better I, just to make sure I don't confuse it, because sometimes if I put the the root 3, and then an I behind it. I'm not sure that's underneath the root sign or not, so typically we'll put the I in front. So what we did, we started with a complex number written in polar form and removed or worked it through, and now we have one that's in rectangular form, a 1 plus an I root 3.